Is gravity truly the smooth bending of spacetime geometry, as we've been taught for so long? According to general relativity, spacetime is imagined as a fabric, with mass and energy causing this fabric to bend. Objects like planets and photons follow the straightest lines within this curved surface, and the event horizon of a black hole is described as a perfect boundary on this smooth surface. Once light crosses this boundary, it can never escape. This is an elegant and highly accurate model, but there are two assumptions left unclear. First, is there an underlying medium beneath the fabric, which is often assumed to be irrelevant? Second, the assumption that spacetime is infinitely divisible and perfectly smooth, which presents issues when considering the quantum realm. In energy filament theory, the foundation is not smooth geometry, but instead a sea of energy that can be stretched, wrinkled, and textured. Gravity, in this framework, is the tension field configuration of this sea at larger scales. It is the overall slope of which parts are tighter and which parts are looser. When you blur the fine details, it is possible to model this as a smooth surface. And this is the geometric appearance we see in general relativity. However, in energy filament theory, the bending is in T of an abstract geometry. The bending occurs in the tension slope itself. This slope, unlike smooth geometry, is granular and rough. These characteristics are not visible in everyday environments like Earth or our solar system, where the forces are gentle, but they become clear in extreme gravitational regions, such as near black holes. As long as the foundation is an energy sea, it's impossible for the surface to be perfectly smooth in the strict mathematical sense. In regions of extreme gravity, such as near the event horizon of a black hole, the tension is stretched to the absolute limit. This tension can cause small disturbances, texture rearrangements, or filamentation processes, which could result in a temporary tension pore where the usual smoothness breaks down. This phenomenon can be likened to quantum tunneling. In the standard interpretation, quantum tunneling occurs when a wave function extends beyond the barrier with a probability of passing through it. However, in energy filament theory, the potential barrier's gravitational or electric potential curve is just its average appearance. The actual underlying structure is a layer of tension that is mostly tight, but it occasionally loosens or tightens, creating a fleeting pore. During this brief moment, the flow of particles reorganizes along the granular structure of the energy sea, moving from one side of the barrier to the other in a way that reduces overall tension. Once the pore closes, this process is completed, and the phenomenon is akin to what we describe as quantum tunneling. The event horizon of a black hole operates under the same mechanism, but this is taken to the extreme. In general relativity, it's thought of as a perfectly smooth point of no return, but in energy filament theory, it's a band of extremely high tension, with a filamental medium underneath and a macroscopic geometry above. The high tension combined with disturbances in the energy sea causes the textures of the tension maps to continually misalign and reorganize on the smallest scales. Tension pores flicker in high density, with each flicker providing an opportunity for particles and photons to sneak through the event horizon. This process allows energy, and even information, to escape from within the black hole. What appears to us as the black hole's event horizon is, in fact, the result of light leaking out through the tension pores, a phenomenon that mirrors the black hole's evaporative effect. Therefore, energy filament theory does not merely add a medium to general relativity and repeat the story of bent smooth surfaces. Instead, it explains three crucial ideas on the same tension sea map. First, on large scales, the geometry described by general relativity is simply the average appearance of the tension slope. Second, at smaller scales, the surface is not smooth at all, but rather covered with flickering tension pores. And third, both quantum tunneling and black hole evaporation occur through structural reorganization and energy leakage along these pores. These processes offer a more intricate and nuanced view of gravity that is not. It only ties together known phenomena, but also challenges conventional ideas about smooth spacetime and gravity's behavior at extreme scales. This perspective on gravity offers a more holistic understanding. showing us that it is not an isolated force but one deeply connected to the other fundamental interactions. Gravity may seem the weakest because it doesn't interact as aggressively with specific elements of the system, yet, its scope is vast. It affects everything, from the smallest particles to the largest cosmic structures. Its influence permeates the universe, quietly shaping the very fabric of reality. In this view, gravity is just one mode of the larger tension sea, with the other forces contributing their own patterns and behaviors, but all ultimately part of the same fundamental process. Tap follow, share it on New Physics, Clear Universe.